Hi class, today's lesson is on the thin lens equation. Um, this equation is used to actually locate an image mathematically. So far we have learned how to locate an image by drawing ray diagrams to show where the light would converge or diverge off of the lens. But that's not the only way that you can locate an image. We can do it mathematically, and today we're going to learn how. So the thin lens equation allows us to predict mathematically the properties of an image produced by a lens. The equation is 1 over dO, which is the distance of the object, plus 1 over di, which is the distance of the image, is equal to 1 over the focus. So 1 over dO plus 1 over di equals 1 over f. And don't be scared of the fractions. F stands for the focal length of the lens. dO stands for the distance of the object, and di is the distance of the image. Here's an illustration of what the terms mean. You'll notice that dO is the distance from the object to the optical center of the lens. The focal length is the distance from the optical center to the focus, and the di is the distance of the image from the optical center. Okay, this is where it can get a little bit confusing, but as long as you have your sign conventions with you while you are doing these questions, you should have no problem. So the distance of the object is always going to be positive, okay, no matter what. The distance of the image, though, is only a positive value for real images, and it's a negative value for virtual images. F is positive for converging lenses and negative for diverging lenses. So this is going to become important because you're going to have to insert the negative values, if you need to, into your equation in order to get the question correct. This table is a really great tool to have with you at all times when you're answering these questions. It's a summary of the sign conventions for lenses, and this includes both for the distance of the image and also for magnification questions, which we're going to get to in a little bit. Okay, so you'll notice dO is always positive, it's never negative. di is positive for real images and negative for virtual images. The height of the object is positive when it's upward, but it's negative when it's downward. Same thing with the height of the image. Focal length is positive for converging lenses, but it's negative for diverging lenses, and the magnification of the image is going to be positive for an upright image and negative for an inverted image. Okay, so copy this down, use it always consistently to make sure that you have the correct signs. Okay. Okay, now we'll get to our first example. A converging lens has a focal length of 25 centimeters. A light bulb is 60 centimeters away from the lens. Where will the image be formed? So if you want to pause the video right now, you can and try and solve this problem on your own. I'm giving you the answer for the distance of the image, and that is positive 43 centimeters. So if you pause the video and plug in your values, see if you can solve this on your own. I'm going to solve it on the next slide for you. Okay, so I always use graphs or guess when I'm solving these problems. So what is given to me right now is that F is 25 centimeters, and I know it's going to be positive because the question says it's a converging lens. Okay. It tells me that the distance of the object is 60 centimeters. We know that the distance of the object is always a positive value, so that's going to stay 60, and we don't know what di is. So what's required of us is to find di. How am I going to do that? Well, I'm going to use my equation. So my equation is 1 over dO plus 1 over di equals 1 over f. Now let's start solving it. I'll solve it in red. So substitute in what you know. dO is 60, so 1 over 60 plus, I don't know what di is, so I'm going to leave it as di, is equal to 1 over 25. Now, don't worry. You can convert these fractions into decimals to make solving easier. So if I take 1 over 60 and I plug it into my calculator, I'm going to get a value of 0.0167. I'm going to ask that you round your values to 4 decimal places for complete accuracy. Okay, so 0.0167 plus 1 over di, we still don't know that, is equal to, if I do 1 divided by 25, that's obviously 0.04, and I can add 2 zeros on the end. Okay, now I'm trying to get di on its own, so I'm going to bring this value over. So what I'm left with is 1 over di is equal to 0.0400 minus 0.0167. When you do that calculation, you should end up with 0.0233. Now, to isolate di, you are going to bring it over to this side, but then this value has to come over to this side. So what you're going to be left with is 1 divided by 0.0233, which is equal to roughly 43 centimeters. Okay, and that was the answer on the previous slide, so I know that I did it correctly. So focal length is positive because it's a converging lens. I substitute in my values, I convert the fractions into decimals, and I rearrange and isolate. Okay, let's try the next one. Okay, our next example is a diverging lens. The question says a diverging lens has a focal length of 30 centimeters. A flower is placed 20 centimeters away from the lens. Where will the image be formed? And again, if you want to pause this video and solve it on your own, the answer that you should be getting is negative 12 centimeters. I will now solve it on the next slide. Okay, let's start solving this problem. So what is given to you in the question is the focal length. Because the focal length is for a diverging lens, the value is actually going to be negative. So this is going to be negative 30 centimeters. The distance of the object, the question states, is 20 centimeters from the lens. We know the distance of the object is always positive, so I'm going to leave that as 20. They're asking us to solve for di, so we don't know that. Leave that as a question mark. And again, the formula that I'm going to use is going to be 1 over do plus 1 over di equals 1 over f. Okay, let's take a different color pen and start solving. So I'm going to start substituting what I know. Do is 20, di I don't know, and the focal length is 30. Now, you'll remember from math that the negative value is for the entire fraction, so I'm going to put it right in the middle there. I'm going to bring this up here. And remember, to make it easier, convert your fractions into decimals and leave 4 decimal places when possible. So 1 over 20 is going to be 0.0500 plus 1 over di, because I don't know that, is going to be equal to negative 1 divided by 30 is negative 0. I'm going to write this very small so it fits, 0.333. Okay? Now, I'm going to start rearranging my equation, so I'm going to bring this over to this side. Negative 0.0333, subtract 0.0500. That is going to leave me with a value of negative 0.0833. We need these two to swap places, okay? And when we do that, it becomes 1 divided by negative 0.0833, which will give you a final answer of negative 12 centimeters, which was the answer on the previous slide. Okay, the second half of our lesson is going to focus on the magnification equation. And remember, lenses magnify objects. So the magnification equation is going to tell us by how much is that magnification occurring by. The formula for the magnification equation is m is equal to hi over ho. or it's m is equal to negative di over do. So I want to make that clear because students often get confused because we write the equation like this. These are two separate equations. If you have the heights, you're going to use hi over ho. If you don't have the heights and you have the distances, then you're going to use negative di over do, or put the negative right in the center for proper notation, okay? So it's one or the other. It's not both. So if you have the distances, you're going to use negative di over do. If you have the heights, you're going to use hi over ho. You're not using all four of these in one question. Okay? And again, m stands for magnification, ho stands for the height of the object, and hi stands for the height of the image. Magnification has no units, so they will cancel out. Okay? Just keep note of that. Magnification equation questions also have sign conventions. So the height of the object and the height of the image are always positive when they're upward from the principal axis. They're going to be negative when they're measured downward. So think upwards positive, downwards negative. And then magnification is always positive for an upright image, and it's negative for an inverted image. And if you refer back to the table from earlier in this lesson, all of this is also written down. That's why having that table with you when you're solving these questions is key. Okay, let's do an example. An iPhone with a height of 11 centimeters is balanced in front of a converging lens. An upright virtual image is noticed with a height of 17 centimeters occurring on the same side. What is the magnification of the lens? So again, pause the video if you would like. You can try and solve it on your own. The answer is 1.545. See if you can get that on your own. I'm going to solve it on the next slide for you. Okay, so what are we given in this question? Well, we are given that the height of the object is 11 centimeters, and we're given that the height of the image is 17 centimeters. They are upright, so I know that they're both going to be positive values. The question is asking me to solve for magnification. Okay, because I have the heights in this question, the equation that I'm going to use is going to be hi over ho. And then I'm just going to simply start solving. And I can solve in a different color. Let's do yellow this time. Okay. The height of the object is 11. The height of the image is 17 centimeters. And you know what? I don't like the color. It's too light, so let's do purple instead. Okay, so we have 17 centimeters divided by 11 centimeters. The centimeters are going to cancel out. You are going to be left with a division problem. 17 divided by 11 is going to give you 1.545, which is simple enough. So the magnification of this image is 1.545. Okay, let's try another one. An iPhone with a height of 11 centimeters is balanced in front of a converging lens. An inverted real image is noticed with a height of 38.5 centimeters on the opposite side. What is the magnification of the lens? And you're going to notice that the answer should be negative 3.5. So you can pause this video and try and solve it on your own, and I'm going to solve it on the next slide for you. So, given we have the height of the object is 11 centimeters. Okay, that's measured upwards. The height of the image, though, it's telling us it's an inverted image. So I am going to put in my value as negative 38.5 centimeters because it's upside down, right? And the question is asking us to solve for magnification. Okay. Again, they're giving us height of the object in the image, so I'm going to use hi over ho. When I start solving, I'm just going to substitute in what I know. So negative 38.5 over 11 centimeters. Centimeters, they cancel out. I'm left with negative 3.5 once I do my division. Okay, let's try another. A toy rocket is placed 12 centimeters away from a diverging lens. An upright virtual image is noticed 9 centimeters away on the same side as the rocket. What is the magnification of the lens? So again, you can pause the video and try and solve it. The answer you should get is 0.75. I'll do it on the next slide for you. Okay, we're going to start solving this problem by listing what we know. So what is given to us in the question? Well, the distance of the object is 12 centimeters. That's always going to be a positive value. The distance of the image, though, and be careful here, it's a virtual image. And so that means that 9 centimeters is actually negative 9 centimeters. So this is, again, why you need to have those sign conventions with you from that table. And the question is asking us to find the magnification. So because the question gives me the distance of the object and the distance of the image, I know I'm using the negative di over do equation for magnification. Okay? So be careful here with the double negative. So magnification is equal to, the equation itself has a negative value, so I'm going to write that first. The distance of the object is negative, so I'm also going to include that, and it's all going to be over the distance of the object, which is 12. These two negatives are going to cancel out, and it's going to be positive 9. So what I'm left with is 9 over 12, which is actually equal to 0.75. So the magnification cancels, the units cancel out, as do the negatives, leaving me with a positive 0.75 value. Okay? So this brings us to the end of our lesson. You have 2 pages of homework. You have page 566, questions 1 to 4, and also 566, questions 5 to 8. So you're doing all the questions from 1 to 8. Okay? Email me if you have any questions.